Okay, so we are looking at our exponent section. We're continuing on with that. But we're going to be looking at what if we have rational exponents and dealing with our radicals and how those actually compare to working with regular fractions. So I know, unfortunately, a lot of people when they get to fractions kind of freeze up, but one thing that's really neat that is if you can connect these two processes together, then the fact that it's a exponent that is a fraction is less intimidating, right? And that's what these notes are going to help you with. So start off, basically rational exponents is another way of expressing exponents as fractions. So put those two concepts together, make it less intimidating, and let's start looking at them. So on a normal fraction, break it down even further. If you look at a fraction and go, okay, this is a two-step operation mixed in one basically setup, that whatever you have, you're going to multiply by 2 and then divide by 3. Or you can divide by 3 first, because order of operations, these two can basically go forward and backwards, usually from left to right. But you can divide first by 3 and then multiply by 2 on a fraction, and you'll get the same exact number as if you multiplied by 2 and divided by 3. So you just kind of work it back and forth depending on which is more practical for the problem that you're actually working with. So a fraction, multiply, divide. So if I have that exact same fraction expressing a rational exponent, what does that mean when we're dealing with, again, exponents and roots? Well, as you hopefully know, is that an exponent just means the process of multiplying to yourself, or the process of getting larger significantly. So addition and multiplication and exponents are all the process of getting larger. Okay? Subtraction, division, and roots and radicals are all the process of getting smaller. So this means basically raised to the power of 2, the second power, and then rooted by 3. So getting larger by 2, getting smaller by 3. Getting larger by 2, getting smaller by 3. So that process and initial basic concept is still the same here. I'm being raised to the power of 2, and I'm going to be rooted by 3, or rooted by 3 and raised to the power of 2. Okay? So again, they're interchangeable here just as they're interchangeable here. So here's another example. Multiply by 3, divide by 5. Or divide by 5 and then multiply by 3. Just as that is interchangeable, our rational exponents are also interchangeable. This is a power, this is a root. We can write it that way, or we can write it as the fifth root of x raised to the power of 3. Okay? They're interchangeable. Process of getting larger, the process of getting smaller. This is just exponentially. So the next concept to look at is adding fractions. Adding fractions with like denominators. You add the numerators, and if you ever get a situation where there's the same number on top, the same number as bottom, then they simplify down to 1. So here, if I have x squared times x to the first power, or x to the 1, remember when you multiply, it's the same thing as adding your exponents. So I get x to the third. Well, this is basically the same concept as multiply by 3. This is basically the same initial concept as divide by 3. So if I'm raising to the third power and then rooting by the third power, they turn into the fraction that looks like this, an irrational exponent of this, which simplifies down to that, and then the x is broken free. So remember that when you have these, your initial rules of, if I was to rewrite this, mn can be written as x to the to the n over m. So this here is your fundamental concept. That's your numerator, that becomes your denominator. That's my power, that's my root. And when they are the same, they simplify. Okay, so let's look at another example. I have 3/5 plus 4/5 plus 7, equals 7/5. Well, I can then break that out and simplify that and say, okay, well, that's the same thing, and regroup it as 5/5 plus 2/5. Still 7 in my numerator, still my fifths in my denominator, but this is going to simplify to 1, and I'm left with 2/5 as what's left over. So if I had something look like this, again, my 3 and my 4, my fifth root, these can combine to make 7, which is being to the fifth root. And then once I combine them, it's kind of like Play-Doh. You can take two things, mix them together, make one large thing, but then you can re-separate it back out as you seem fit and as you want to do it. So I can then rearrange my exponents to make it an x to the fifth and an x to the second. And then what I have, if I was to then break these into two separate radicals, I would have the fifth root of x to the fifth, which simplifies down to just x to the 1, and the fifth root of x squared. And that is what I'm left with. And so here again, you can see the x to the 2/5 and x to the 1, exactly like my fractions. So let's look at another example of how fractions and radicals are very similar. So we have 3/4 of 8. So again, we're going to multiply my numerators, because this is just 8 over 1. Then divide, multiply by 3, divide by 4. That's all the fraction says. So what if I have 8 raised to the power of 3/4? Well, then I'm going to rewrite it. Instead of as a rational exponent, I'm going to rewrite it as a radical. Here's my numerator is my exponent, my denominator as my radical and my root, basically. And then just like here where I said, well, I'm going to multiply, here I'm going to do my exponent, 8 times 8 times 8. And then I can take the root of it, which is approximately 4.76. So that is how you can do the same initial concept. Here we divided by 4, here I rooted by 4, here I multiplied by 3, here I raised to the power 3. The initial process is there. It's kind of revved up one level with the exponents, but the concept is there. Okay. So what if I was to do this first using my division and then multiply? Because I said, remember, you can multiply by 3 and then divide by 4, Or you can divide by 4 and multiply by 3. Does it change anything? And as you see, the answer is no. You still get 6. And here, if I was to take the fourth root of 8, which is approximately 1.68, and then I cube it, I still get approximately the same answer. So it's true with fractions. It's true with our rational exponents. So let's look at another way that these are similar. So I say 1/5 plus 2/5 equals 3/5. Boom. Okay, add the numerators, denominator doesn't change. Well, with exponents, if you remember that x to the m times x to the n equals x to the m plus n. So if this was x to the, let's just say 8th, and x to the 4th, then we'd get x to the 8 plus 4, or x to the 12th. Fundamental exponents. If they are rational and fractions, the process doesn't change. This meets this. That is it. This exponent is going to be added to that exponent. M just happens to equal 1/5. N just happens to equal 2/5. So I'm going to add them together like I would any other exponent, and I just end up with 3/5. So you see here, you're multiplying, you add the exponents together, and you can either leave it as a rational exponent or you can rewrite it as a radical. This is my exponent, that is my root. And we're done. Don't make it more complicated than it needs to be. It's just this. Okay, so what if we're multiplying? So I have 1/2 times 2/3. What do? You multiply the numerators, you multiply the denominators, you get 2/6. I can then simplify out the base of what I like to call the fraction equivalent to 1. Some people call it a unit fraction. And I'm left with 1/3. So if you have something that looks like this, this breaches off of the exponent rule that says x to the m raised to the power of n. And for space, if you'd like for a little bit of review, I can also put it over here. That x to the m raised to the power of n is just x to the m times n. Okay? Sloppy over there, that's right. Okay? Or mn. So if it's raised to the power, that means we multiply. So if it's raised to the power, that means it's multiply. Hey, look, this here just looks like a miniature version of this over here. And because of that, the process isn't going to change. I'm still going to multiply my numerators. I'm going to multiply and divide by the multiplication of my denominator, basically. Multiply my numerators, multiply my denominators. I get my rational exponent, which again can simplify exactly like over here down to 1/3, which if I'm being asked to write it as a radical, I can rewrite it as raised to the power of 1 rooted by 3, and I'm done. So this is a fancy way of this. Basically, you ignore the x and just treat it, I can squeeze my finger and squeeze it as the multiplication of fractions is what the problem is. The x just happens to be there. as the base number. So what about division? Again, same initial process. We do the multiplication inverse, we flip it. We multiply across. Reciprocal. And simplify. So what if I have this divided by this? It looks really complicated. You're like, oh my goodness, not only do I have exponents, I have fractions in my exponents. And not only do I have exponents that have numbers with fractions and exponents, they're now being divided by another number that has a fraction in its exponents, making it a really oversized fraction. But don't. This just means division. That's all it means is division. So then you just go, okay, well, it's 1/2 divided by 2/3. Oh, I know how to do that. Hey, look. It's x to the 3/4. Okay? So don't overthink it. I have a little last bit note of reminder here that x to the -2 is basically the same concept as 1/x squared. And with that, it's the same thing here. The x to the negative of a fraction is 1/x to that fraction, which then you can rewrite as 1 over the radical. All right. Well, I hope this helped.